Hi trig students, this is section 9.3. It's called the complex plane. We're going to go through this and then just two more sections and our content will be done. So first thing we're going to do is just get rid of this little phrase here at the end of the complex plane title where it says vector representations. We're not going to worry about vectors just yet. In section 9.4, we are really going to get involved with vectors, so we're not worried about that right now. Okay, let's talk a little bit then. So, in the complex plane, we graph complex numbers. You are used to seeing complex numbers that look like this in algebra. They have real parts and they have imaginary parts. So, when we graph this on the complex plane, we are going to need a real axis. This is what the x-axis is now called, is the real axis. And we're going to need an imaginary axis, and that's what the y-axis is now called, is the imaginary axis. Okay, so these are where the real numbers are going to go, the first component. These are where the imaginary numbers are going to go, the second component. Now there's three ways to write these complex numbers. There's rectangular form, which you see right there, x plus y I. So anytime you see x's or y's, we are in rectangular form. There's also polar form, sometimes called trig form, that looks like this. Okay, and z is just how they like to abbreviate a complex number. So we have cosine theta plus I sine theta. Remember, in rectangular form and algebraic form, the I comes last. In polar form or trig form, the I comes before the sine. Now sometimes, because this is very lengthy, we abbreviate it as cis theta. The C is from the cosine, the I is from the imaginary, and the S is from sine. And there's the theta, because these thetas are the same. So if you see cis theta, it actually means cosine theta plus I sine theta. All right, if we add that little r in there in the front, then we get r cis theta. Okay, now a new form that we sometimes use is exponential form. This is very helpful and it's very compact. It's easy to write and it has all your information. So according to Euler's formula, e to the I theta, these are both little exponents on the e, is the same as cosine theta plus I sine theta, which means that z equals r times e to the I theta, okay? All right, now we've been talking a lot about r. R is also called the modulus or the magnitude of the complex number. This is how you get it. The magnitude of that complex number is just going to be x squared plus y squared. So this, which we already know from the last section, is equal to r. Okay, and the angle theta is called the argument of the complex number. So these items that I have highlighted, remember, those are my math lab questions. So I wanted to make sure those stand out for you. That'll take care of about the first 5 questions on my math lab. All right, so what we're going to spend this packet doing is graphing in the complex plane and then going back and forth between these 3 forms. So remember, if x is r cosine theta and y is sine theta, I could put that right into x plus yi. I can put r cosine theta in for x, r sine theta in for y. I can pull out that common r and I can move this I to the front, and suddenly I have polar form. So that works out really well, okay? The only other formulas we need to talk about are on the next page. Now these formulas we actually won't need until we get to the last 3 problems in this packet, but I thought I would go ahead and put them there just so that we have them. The first is the product theorem. So we use the product theorem when we have 2 complex numbers in polar form and we want to multiply them together. So we would take their two r's and multiply them, and we would take their two thetas and add them. And that's how you get the product. Okay, similar for the quotient theorem if we had two complex numbers. Now, with division and subtraction, you know that it's really important for the order to be maintained. So the first r is going to be divided by the second r. First r is your numerator, second r is your denominator. Then we're going to subtract these thetas. We're going to take the first theta from the very first complex number minus the second theta. And that's where that goes. Now you can also apply these to exponential form. They're really quick and easy when you do it that way. For the product theorem, we multiply the r's, we add the thetas, still an exponent. For the quotient theorem, we divide the r's, subtract the thetas, still an exponent. We'll practice that more at the end. Okay, so let's jump right into our examples. We have quite a few. This is the longest section we have left, and then 9.4 and 9.5 are pretty fast. So here we go. Example 1, find the complex conjugate of the given complex number. Well, this is good old algebra. It's been a long time, but hope you remember that the complex conjugate just means that we are going to change the sign of the imaginary portion. So I'm going to leave the 9 alone. Because this is plus 5i, the complex conjugate is going to be minus 5i. And that's your answer. If this were minus 5i, we would make it plus 5i. But we never change the first number. We leave him alone. Whatever he is gets to stay. Okay, so that's just a little blast from the past. All right, let's jump right into trig then. All right, first thing we're going to do, example 2 wants us to plot the complex number on the complex plane. Then we're going to come down here and write it in polar form and exponential form. Okay, here we go. So I notice here, because remember, this is the form we've been given, rectangular form, that x is equal to 9. That's the real portion of the number. Y is also equal to 9. That's the imaginary portion of the number. So we are graphing 9, 9. So I'm going to go positive 9 on the real axis, positive 9 on the imaginary axis, and I'm going to place a dot. That's all you have to do. So on my math lab, all you're going to have to do is click right on that dot. Now, it's also really important that you make a note somewhere telling what quadrant that point is in. That's going to come in handy when we're trying to match up our polar form. So this is quad 1. I'm just going to remember that. Okay, now we're going to write it in polar form and exponential form. We are going to type the exact answer using pi. We are going to use radians for any measure. So make sure you're in radian mode. You should be in function and you should be in radian under mode. Okay, we're no longer messing around in polar. Okay, even though we're doing polar form. All right, your angle measures should be positive and within 1 rotation. No decimals. Here we go. Well, first thing we're gonna need is an r. So if you recall, r is x squared plus y squared. Well, here's our x's and y's. So I'm gonna have 9 squared plus 9 squared. That's going to be 81 plus 81. That gives me a square root of 162. Okay, that's not a perfect square, but we can reduce it. If you're comfortable reducing radicals, you know that your r is 9 root of 2. If you're not so comfortable doing that, remember you can make a little factor tree where you just divide a number into it. If I divide 2 into 162, I get 81. Now some of you can take it from here. Square root of 81 is 9, 2 stays under. Or the idea of a factor tree is that you keep breaking down these numbers. Now the 2 doesn't break down, that's why he just follows all the way to the bottom. But you keep breaking down these numbers until you have all prime numbers there, which is what we have. Then I know I'm looking at a square root, which has an index of 2. I want to circle numbers that have 2 of the same number. 2 numbers here, 2 numbers here. I pull out 1 of each, multiply them together, I get 9. What's left is the guy that wasn't circled, and that's where that came from. So that is just a little reminder of how to do that, and this was your mode that you're supposed to be in. Okay, all right, so we have R. Now we're gonna need theta. Now this book likes to use tan theta. Now you can absolutely use tan theta, and we're actually going to do that as well, but I think it's easier to also find cosine theta and sine theta. I think it's easier for students to find on the unit circle, especially since we're dealing with radians. So I'm just going to kind of show you all the different ways, but if I were going to find cosine theta is x over r. My x is 9. My r is 9 root of 2. If I clean that up, I get 1 over the root of 2. Now I'm going to have to rationalize that, and I get root of 2 over 2. All right. If I find sine theta, that's y over r. Y is 9. R is 9 root of 2. This also simplifies down to 1 over the root of 2. Okay, I rationalize and I get root of 2 over 2. Now I know I'm in quadrant 1. So now I'm looking for the theta in quad 1 that matches up with this point, my cosine and my sine. So I would then go to my unit circle. I would look in quadrant 1. Here's that point. Here's cosine. Here's sine. There's my theta, pi over 4. Okay. So theta is pi over 4. Now, the book would like for you, rather than doing it this way and looking at a point, they would like for you to use tan theta, which is y over x. If I do that, I see that that's 1. So they like for you to think a little more abstractly. They would like for you to go into quadrant 1 and find where is tangent equal to 1. Well, remember, tangent's not explicitly on here. So tangent is sine over cosine, or y over x. So you would have to look at these points and find the one that if you put y over x equals 1. Now that's pretty easy because this is the only one that has both x and y the same, so they'll cancel down to be 1. And that's how we get pi over 4. It gets a little more complicated when we're looking at something else though. But this is kind of how the book likes to do it. And then you would also come to the same conclusion that theta is pi over 4. Okay? All right. So now we want to write in polar form. So if you recall, polar form is r times cosine theta plus I sine theta. It's always like this, and the thetas are exactly the same. Well, we have our r, it's right here. We have our theta, it's right here. Okay, and here we go. There's your answer. Now, we also want this in exponential form. Okay, so if you recall, exponential form is r e to the I theta. Okay, make sure you can see that. Scoot it over a little bit. Okay, so if I do that, my r is 9 root of 2 e to the I pi over 4. That is my polar form, okay, where I have my r's. I have I and pi over 4 are both exponents right there. And there we go. Okay. All right, let's keep practicing these. There's a few more. They each have a little something different, so I want to make sure you're comfortable with them. All right, we're going to do the same thing here. We are going to plot the complex number, and then we're going to write it in polar form and exponential form. Okay, so here we go. I notice that my x is 12 root of 3. That's my real portion. Now, if I put that into the calculator, that ends up being like 20.78, just to give you an idea of what 12 root of 3 really is. And I have a y of negative 12. That's my imaginary part. So when I go to graph this, I don't really have a great fit on my little graph here because this only goes to 9. So I'm actually just gonna get rid of these little numbers here. I'm crossing them out. And I'm gonna make each one of those little numbers 2. So 2, 4, 6, 8, 10, 12, 14, 16, 18, and this very last one is 20. Okay, I'm not gonna worry about these over here. And we could leave these. In fact, I'm just gonna go down a little bit more till I get to a negative 12. So it's not a great little grid for this particular example, but it's all I could find. Okay, so if I'm gonna plot this, I'm gonna go positive 20.78, okay, which would be about here, and down 12. So I don't know, I'll say about there. On my math lab, it's gonna be really clear and nice and easy, and so it'll work out well. Okay, there's my point. I also wanna make a note, my point is in quad 4. That's important. Okay, now we have r equals. So remember, r equals x squared plus y squared. So here is x squared, and here is y squared. Okay. All right, now 12 squared is 144. Root of 3 squared is 3. So 144 times 3 is actually 432, plus another 144 from here. Okay, that's the square root of 576, and believe it or not, that's a perfect square. Your r is 24. How about that? All right, so now I'm going to find my theta. So I'm going to say cosine of theta is x over r. Okay, if I clean that up, that is root of 3 over 2. I'm going to say sine of theta is y over r. Clean that up, it's negative 1/2. So now I'm going to find a theta in quad 4 that has the point root of 3 over 2 and negative 1/2. Okay, so I'm going to take my unit circle. I'm going to look in quad 4. Okay, I'm looking for root of 3 over 2, negative 1/2, and I want the radian measure. It's 11 pi over 6. That is going to be my theta. Okay, now again, that's not exactly how the book teaches it. The book likes for you to only use tan theta. Why is that? Well, r is something you came up with. And so remember, if you use a quantity that you came up with, there's a chance it could be wrong, and then everything based on that is wrong. You won't go wrong if you use what's given. So they like for you to use y over x because it's given. You end up there, okay? So remember, tangent is y over x, so where in quad 4 would you have a y over x that would give you this? Well, just so happens to be at this point. If I have negative 1/2 over root of 3 over 2, the 2's cancel. Sure enough, that's 11 pi over 6, but this is a little harder to see. So would you be able to know that it's 11 pi over 6, given that your tangent is negative 1 over root of 3? Okay, so that's a little harder. That's why I think students like this way a little bit better, but either way, get your theta. Okay, now we want polar form. R is 24 times cosine of 11 pi over 6 plus I sine of 11 pi over 6. There it is. That's all you got to do. Okay, exponential form, R times e to the I times theta. And there's your exponential. So it's not hard at all. The trickiest thing is theta. Okay, but just make sure it lines up in the quadrant that you want it to be in. All right, let's look at example 4. Okay, so now this looks a whole lot like example 2. Example 2 was actually 9 plus 9i, so we're just going to be a little bit different here. Our x, our real part, is positive 9. Our y part, our imaginary part, is negative 9. Okay, so we are looking for positive 9 on the real axis, negative 9 on the imaginary axis. Brings us down here. Sure enough, we're in quad 4 one more time. Okay. All right, directions are the same. I should have been pointing that out, but they're the same. Radians with your theta positive within one rotation. Okay, so our r is going to actually be the same r as example 2 because we have 9 squared plus a negative 9 squared. That's going to give us 81 plus 81, which is the square root of 162. Okay, now remember, we already did that. We decided that it was 9 root of 2. We looked at how that worked out. Now, just because we have the same r does not mean we are going to have the same polar and exponential form, because this point was in quad 1. We are now in quad 4 because we have a minus. So just keep that in mind. But I am going to just say, okay, r is 9 root of 2, because that is what the square root of 162 is when we reduce it. Okay, so now I like to do the cosine theta, which again is x over r. Okay, I'm going to have to rationalize it in this case, and it becomes root of 2 over 2. I'm going to find sine theta, negative 9 over 9 root of 2. That's y over r. This becomes negative 1 over the root of 2. If I rationalize it, I get negative square root of 2 over 2. So now I want to find theta in quad 4, and my point is root of 2 over 2, comma, negative root of 2 over 2. Okay, so quad 4, root of 2 over 2, negative root of 2 over 2. This has to be my theta, 7 pi over 4. Okay. All right, now if we had decided to do tan theta, that would have been y over x. We would have been looking for a tan theta equal to negative 1 in quadrant 4. Well, that also would have led us to 7 pi over 4 because y over x would have reduced down to a negative 1. Okay, so our polar form is going to be r times cosine 7 pi over 4 plus I sine 7 pi over 4. And there's our answer. Okay, our exponential form is going to be r e to the I times theta. There we go. All right, now I know you're probably tired of doing this already. We're going to do one more simply because every theta we have tried to find has been on the unit circle, which has been lovely, but that doesn't always happen. So this particular example is going to be a good one to do because the theta is not found on the unit circle. We're going to have to use our calculator, and I want to make sure that you're comfortable doing that. So last one of these, and then we're going to do some other things. Okay, so my x is negative 7. My y is 10. I'm looking for the point, negative 7, positive 10. So I'm going to say 10 is way up here. And that puts us right there. Okay, that's in quad 2. Easy enough. All right. Now notice the directions here. The directions kind of tell us, uh-oh, there's a problem. It says to use radicals as needed. Type any angle measure in radians, rounding to 3 decimal places. That tells us we're going to have to use our calculator. And then, of course, to be positive and within 1 rotation. So that's new, the 3 decimal places. Okay, well, let's go ahead and see what we get. We need an R either way. So we're going to have -7 squared plus 10 squared. It's going to be 49 plus 100. We get the square root of 149. Now, I know that this looks like you ought to be able to reduce him, but you actually can't. This is as reduced as it gets. There's just nothing to put into that to reduce it in any way, and you can play with that on your calculator. You can keep dividing and keep dividing, but nothing is going to come out of there. It is what it is. So, okay, now we can do cosine and we can do sine if you want to on here, but we are not going to be able to find anything that looks like this on the unit circle. I think seeing that as your R and this is your X and this is your Y, I think you realize this is not on the unit circle. So let's go over to tan. That's Y over X. Now you could do this with any, you could do it with cosine, you could do it with sine, you can do it with any theta that you want to, but let's just do it with tangent. That's what it recommends. So 10 over -7. So obviously that is not a unit circle number. Okay, not on unit circle. Okay, so that means we're going to have to use our calculators and we're going to have to use inverse tan. Okay, we're in radian mode and inverse tan. So let's write that over here, rad mode, just in case you're not. All right, now I'm going to get rid of this negative. I don't want to worry about a positive or a negative because what I'm going to end up finding here is a reference angle. So even though this is a negative, this tells us what quadrant it's in. I'm going to make this a positive. So I'm going to take my calculator, okay, and I'm in radian mode. All right, I'm going to do second tan, 10 divided by 7, and I get this decimal. This is not your theta. This is your reference angle. Remember good old reference angle there that we used sometimes? This is your reference angle. So your reference angle equals 0.96007. I'm just going to take it out quite a bit. All right, so let's see if we can remember what to do when we have a reference angle. Okay, I'm just going to draw it right here. If you have a reference angle and you want in quad 1, you're good to go. That is your angle. If you're in quad 2, you're going to have pi minus your reference angle. If you're in quad 3, you're going to do pi plus your reference angle. If you're in quad 4, you're going to have 2 pi minus your reference angle, okay? We happen to be in quad 2. That's where we want to be. So our theta is going to be pi minus 0.96007. Now we're going to round it to 3 decimal places. So I'm going to do pi minus 0.96007, and I'm going to round it 2.18. Oh, 2.182, actually, sorry. 2.182 degrees. That gives me 3 decimal places. This was a 1, but the 5 next to it moved it up. That is my theta. So your polar form is ugly, but it's correct. So root of 149 cosine 2.182 degrees plus I sine of 2.182 degrees. There's your polar form. Your exponential form is going to be R times e to the I, 2.182 degrees. And there it is. I know that's a little strange with that I in the front there, but that's That's just the form, okay? All right, so that reference angle business was a little tricky. That's always going to be around and come back to haunt you. Anytime you're not on the unit circle, that's when you have to deal with that. Okay, let's go on and do some other things now. I think we've done that part enough. Okay, now we have the polar form. We want to write it in rectangular form. Okay, well, I have R right there. I have theta right there in two different places. Okay, so remember, rectangular form, what we're looking for is x plus yi. That's what we're looking for. Okay, x equals r cosine theta, y equals r sine theta. So there we go. Okay, we're going to plug in what we know. R is 14 times the cosine of 5 pi over 3. Y is going to be 14 times the sine of 5 pi over 3. Okay, x equals 14. Now, so when we go to our unit circle, we find 5 pi over 3, and we want to be able to put that value in for cosine and for sine. So here's my unit circle. I look for 5 pi over 3, and here he is. He's down here. He's equivalent to 300 degrees. Here's my cosine. Here's my sine. Okay, so cosine is 1/2. Sine is negative root of 3 over 2. Cosine is 1/2. Sine is negative root of 3 over 2. Okay, now I'm going to clean it up. This becomes a positive 7. This becomes a negative 7 root of 3. Now I'm going to write it over in this form. 7 minus 7 root of 3 I. All right, the very last thing we're going to do is verify the placement. So 5 pi over 3 was in quadrant 4. Remember, that's where we got this point from. If I were to graph this on the complex plane, I would go positive 7, negative 7 root of 3. That's also quad 4. So that's a good indication that we did it correctly. Just another little checkpoint you want to make sure that you have. Okay, here we go. We have an R and we have a theta. All right, we're going to do the same thing that we did. So we're looking for x plus yi. Our x is 6 cosine of 3 pi over 2. Our y is 6 sine of 3 pi over 2. Okay, now we're going to go to our unit circle. 3 pi over 2 is not a quadrant. 3 pi over 2 is a quadrantal, right? It's down here on the negative y-axis. So here's our point. Our cosine is 0 and our sine is negative 1. So cosine is 0, sine is negative 1. There we go. So now 6 times 0 is 0. 6 times negative 1 is negative 6. All right, if I put this in rectangular form, I don't have an x component. All I have is negative 6. Whoops, I don't know why I put I. Sorry, guys. I. There we go. That's it. I didn't have an x, it was 0, and my y was negative 6. Okay, does this make sense? Well, we said that root of 3 over 2 was this negative y-axis, right? We said this is it. All right, if I were to graph this, I wouldn't go left or right because I have a 0 for x, but I would go down 6. Sure enough, that would also land right there on that negative y-axis. So, sounds right to me. Okay. All right. Example 8. Okay, this one's a little different. So, we're going to have to think about this again. We have an R, but it's a weird little decimal, right? And we have a theta, but that is not a theta that's on our unit circle. So we're going to have calculator. Okay, notice it says do not round until the final answer, then round to the nearest thousandth. So this knows we're going to have decimals. Okay, so x is going to be r cosine theta. Y is going to be r sine theta. Okay, so we're going to have our calculator. We're in radian mode. Here we go. For x, we're going to have 0.9 times cosine of 8 pi divided by 9. Here we go. Okay, little strange here, right? But that's okay, that's what it is. X equals negative 0.846. Okay, thousandth means 3 decimal places. All right, to get our y, here we go. We're going to have 0.9 times sine of 8 pi divided by 9. 0.301. Nope, I'm sorry. 0.308. It's going to round up to an 8. 0.308. Okay, and now we put this into rectangular form. It's strange looking, but again, it is correct. And there we go. Now, if we wanted to check, if we were really concerned, and this was a test, and we wanted to make sure that we were on the right track, okay, 8 pi over 9. Well, I know this is pi, which means I can make it anything I want. So I could make this 9 pi over 9. All right. 8 pi over 9 sounds awfully close to 9 pi over 9. So I'm guessing it's over here in quadrant 2. Okay. Does this line up in quadrant 2? Let's see. I have a negative x and a positive y. Yep. That is also quadrant 2. So it looks like we're on the right track to me. Okay. Now we want to also write this in rectangular form, for example, 19. We don't have, though, polar form anymore, but that's okay because we have r, it's a 9, and we have theta, it's pi over 15. We don't actually need polar form. You can write it in polar form if you want to, but we just need rectangular form. All right, this does not look like the unit circle any more than this did. And this is telling us to round to 3 decimal places, so it looks like we're using the calculator again. Okay, x is going to be 9, that's r, times cosine of pi over 15. Y is going to be 9 times the sine of pi over 15. This is going to give me, I'm going to use my calculator again, 9 times cosine pi divided by 15. There we go, 8.803. Okay, we're going to do the same thing for y, and you would get 1.871. Okay, put this together in rectangular form. And there we go. Okay, again, if you wanted to check this, see if you were on the right track, pi over 15, that's 1 over 15. That's an itty bitty little angle. So that's definitely a quadrant 1 angle. Okay, do these coordinates go with quadrant 1? Well, x is positive, y is positive. Sure enough, that is also a quadrant 1 situation. All right. Last but not least, we have these 3 problems in the back. These 3 problems deal with the product theorem and the quotient theorem. We want to take these 2 complex numbers in polar form. We want to find the product of them and the quotient of them. We want the answer in polar form and the answer in exponential form. Okay, well, I like to go ahead and put them in exponential form, then multiply or divide them, and be done with it. I just find that easier than trying to mess around in polar form because those forms are so long. So here we go. For z, let's talk about the fact that he has R1, it's 7. This theta that you see here is theta 1. It's 5 pi over 9. Now, why are both of these guys 1s? Well, because it's the first one you see. Okay, W is going to have R2, which happens to be 35, and it has theta 2, which happens to be pi over 9. Okay, now I'm going to rewrite both of these in exponential form. So my Z is going to turn into 7e to the I times 5 pi over 9. And W is going to turn into 35e to the I pi over 9. Okay, now I'm going to multiply them. Z times W is going to give me R1 times R2, e to the I, theta 1 plus theta 2. That is my formula. Okay, let's scoot it over a little bit. All right, so ZW is going to be 7 times 35, just multiplying these guys together. E to the I, I'm going to have 5 pi over 9 plus pi over 9, because those are my two thetas. Okay, I just added them together. You don't actually need to label them if you don't want to. Okay, so what does this give me? 7 times 35 is 245. E to the I, 5 pi over 9 plus 1 pi over 9 is 6 pi over 9. We can reduce that though, and ZW should be 245. E to the I can pull a 3 out of the top and the bottom, 2 pi over 3. That is exponential form of ZW. Now, I'd also want polar form. So if I were to rewrite this in polar form, here's my R out front, cosine of 2 pi over 3 plus I sine of 2 pi over 3. And I just wrote it in polar form. Okay, so I rewrote both of these in exponential. I followed this formula, filled in my amounts, multiplied my R's together, added my thetas, and then reduced that. This is my exponential form of ZW. Then I took this and made it into the polar form. Here's my R, here's my theta. Okay, now let's talk about Z divided by W. This is going to be R1 divided by R2 times e to the I, theta 1 minus theta 2. Okay, so we're going to have 7 divided by 35. Okay, we'll have to reduce that in a minute. E to the I. Then we're going to have 5 pi over 9 minus pi over 9. Okay, 7 divided by 35 is 1/5 times e to the I, 4 pi 9 over 9. There's our exponential form of Z divided by W. Okay, now if I were to write this in polar form, whoops, I've already written the multiplication one. How about division? Okay, here's my R, 1/5. I've got cosine of 4 pi over 9, that's my theta, plus I sine of 4 pi over 9. And there we go. All right, all 4 answers. Okay, let's do it again. We've got 2 more of these we're going to practice with. Okay, same directions down here. The only difference is all of these thetas had the same denominator up here, right? These don't. So we're going to have to get a common denominator when we go to add and subtract them. So that's the next step here, is making sure you're comfortable with that. Okay, let's write these in exponential form. Now you can go ahead and label them all if you want to. I'm going to write them in exponential form. I'm going to say 7, that's my r, e to the I, and my theta is pi over 9. Okay, that's z. My w is going to be 7, same r, e to the I, but now my theta is pi over 13. All right, well, before I go any further, I know I'm going to have to add these guys and subtract these guys, so I need them to have a common denominator. Well, 9 and 13 just so happens that the least common denominator is if you multiply them together and you get 117. So if I take pi over 9 and turn him into something over 117, I'm going to multiply top and bottom by 13. He becomes 13 pi over 117. If I take pi over 13, multiply him by 9 top and bottom, I get 9 pi over 117. Okay, so from this point on, I'm going to use these thetas in place of these, just because that way they have a common denominator. Okay, all right, let's look at z times w. For z times w, I'm going to multiply these together. So 7 times 7. If you want to go ahead and put 49, you go for it. E to the I, and then here's my first theta, it's pi over 9. That's actually 13 pi over 117 plus pi over 13, which is actually 9 pi over 117. Okay, if I clean this up a little bit, I get 49 e to the I, and that becomes 22 pi over 117. That is a very strange answer, but it's right. There we go. Okay, if I write this in polar form, here's my r times cosine of 22 pi over 117 plus I, sine of 22 pi over 117. And there we go. Ta-da. Okay. All right, let's divide. I'm going to have R1, that's the first one, the z, over R2, that's the second one, that's from W, times e to the I. Then I'm going to have the first theta, 13 pi over 117, minus the second theta, 9 pi over 117. I'm going to clean that up. This is going to reduce down to 1, so I don't have a coefficient. E to the I, 13 pi over 17 minus 9 pi over 17 is 4 pi over 117. There's our exponential form. Now, if I were to write the polar form, I don't have an r out front, okay? So you don't have to put parentheses, or you could, it's up to you. Cosine of 4 pi over 117 plus I, sine of 4 pi over 117. And there we go. Okay. Hopefully you're realizing it's not as bad as you might have thought it was. It's just a formula. You're just plugging in the numbers. It's not hard, but you do need to practice and make sure you're comfortable. Okay, very last problem for this section. Same directions, except now, instead of being given polar form, we have been given rectangular form. So we have an extra step. Okay, but it's the last problem, so we can do it. Before we can do, I'm gonna fold this paper a little better. Before we can do this though, we have got to write both of these in in polar form. We have to write them both in polar form. So first thing we need to do, let's focus on Z. We're going to need an R for him. He would have an R1, right? Okay, that would be 7 squared plus a negative 7 squared. It's going to be 49 plus 49. That ends up giving us square root of 98. Okay, which means we can reduce this 7 root of 2. Okay, if you need help breaking that down, take your 98 and break it down, divide it by 2, you get 49, and then you can break it down from there. Okay, all right, if we take W and find R2, we're going to have the root of 3 squared plus a 1 squared. Square root of 3 squared is 3, plus 1 squared is 4, plus 1 squared is 1. 3 plus 1, square root of 4, that's a 2. Okay, so we have both of our r's. All right, now we need a theta for each. Let's go back and start working on z. That would give us theta 1. Okay, so tan of theta 1 is going to be, okay, we better go over here and write this. X is 7, y is negative 7. So y over x, negative 1. Okay, you know what we didn't do is we didn't take into account the quadrant that each one of these is in. What quadrant is z going to be in? We have a positive 7 and then a negative 7. This is quad 4 for z. For w, we have a positive root of 3 and a positive 1. W is in quad 1. Okay, so here I'm looking at theta 1. I'm looking for z's theta so that I can write him in polar form. So I'm looking in quad 4 for a tan theta that equals negative 1. Okay, here's my unit circle. I'm in quad 4. Tan theta is negative 1. That means that your sine and cosines canceled except for a negative sign. So your theta is 7 pi over 4. Okay, so theta 1 is 7 pi over 4. There we go. Okay, now let's turn to W. We need a theta 2. So we're going to have tan of theta 2. Here's our x, here's our y. We're going to have 1, that's y, over root of 3. Okay, so this is in quadrant 1, where tangent theta equals 1 over square root of 3. Okay, we have to think about this. Quadrant 1, it's not going to be pi over 4 because that would have a tangent of 1. It's going to be one of these two. Tangent is y over x. Where is our root of 3? This y over x would put the root of 3 in the numerator. This y over x would put the root of 3 in the denominator. Here our root of 3 is in the denominator. I know we haven't rationalized yet. That means our theta is pi over 6. Okay, so theta 2 is pi over 6. Guess I should have written it over here. There we go. Okay, now we can put this together a little bit. Let's take z. Let's write him in exponential form. His r is 7 root of 2 times e to the I times 7 pi over 4. That's his polar form. Okay, let's look at W. His r is 2 times e to the I times theta, which is pi over 6. Okay, now we can finally find the product. So all of this was just getting us to this point where we have two complex numbers in exponential form. Okay, now we're going to multiply 7 root of 2 times 2. E to the I, we're going to add these thetas together. Okay, well, guess what? They don't have the same denominator. So a common denominator for 4 and 6, I know some of you are saying 24, you can use that if you want. The least common would be 12. So if I take 7 pi over 4 and I want to turn it into something over 12, I'm going to multiply top and bottom by 3. That's 21 pi over 12. If I take pi over 6, turn it into something over 12, that's going to be 2 pi over 12. Okay, so this theta plus this theta is going to be 21 pi over 12 plus 2 pi over 12. Okay, z times w is going to be 14 root of 2. Okay, these multiply together. You can't do anything about that number under the radical. E to the I, 23 pi over 12. There's your exponential form. If you wanted to write that in polar form, here's your r, cosine of 23 pi over 12 plus I, sine of 23 pi over 12. There we go. Okay. All right, let's do a division. Now we're going to have z divided by w. All right, so now we're going to have r1 divided by r2. Okay, nothing we can reduce there. It's just ugly, but there it is. Okay, times e to the I. And now we're going to have the first theta minus the second theta. So this theta minus this theta. We're going to have 21 pi over 12 minus 2 pi over 12. That's going to give us 7 root of 2 over 2. Remember, I can't reduce this because this 2 is under a radical. Times e to the I, 19 pi over 12. There's the exponential form. If I wanted to write it in the polar form, here's my r, parentheses, cosine 19 pi over 12 plus I, sine of 19 pi over 12. And there we go. We did it. We finished. Okay, I know that was a lot of work. If you were just watching and following along, maybe not so bad. If you were writing it out like I was, your hand probably hurts. So that is the end of 9.3. 2 more sections to go. Hang in there. I hope you're staying healthy and I miss you. Bye.